Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at ionization energy. So this is a simple term to help depict how much energy it takes to remove an electron from a pure element. So a good way to look at ionization energies is it's a good measure of how happy an element is. The happier an element is the way it is, the less likely it is to want to lose an electron, and thus the higher the ionization energy. We can try and depict this numerically by, again, how much energy do I have to put in to remove an electron? And we can approximate this using our good old friend Z effective. So the energy of an orbital is going to be essentially the negative of the ionization energy. As far as the orbital is low in the potential energy surface, that's how much energy you have to overcome to remove it. And so thus we can depict the ionization energy using the Rydberg constant, the squared of our Z effective, and the electronic shell that I'm removing the electron from. Because again, the lower the shell, the deeper in I have to reach to remove that electron, the harder it is. However, if it's sitting way far out in some excited shell, it's going to be fairly easy to pull off the electron. And what we end up having is a lot of dueling behaviors in between this Z effective trends and our electronic shells. And this is really going to control a lot of the periodic trends we see for ionization energies. And again, this is also makes ionization energy a pretty good measurable depiction of orbital stability. Higher the ionization energy, the more the stable the orbital. So what we're doing is essentially looking at the energy it takes to go from having, say, a full shell for argon to slowly losing an electron. Every electron lost will have a different energy associated. We're going to start by looking at first ionization energies. So this is to go from the neutral element to the +1 cation. And what we tend to see is for these first ionization energies, they tend to increase with Z effective. So the higher the Z effective, the harder it is to remove the electron, but they also tend to decrease with N. So if I go from hydrogen to helium, we see a big increase in ionization energy. Same thing when I go from fluorine to neon or chlorine to argon. So we tend to see this general upward trend through each of my periods. However, you may notice that we see these huge drops every time we go to a higher shell. And this is because that the principal quantum number sits in that denominator as a squared. So when you go from a denominator of 1 to 4, you have this huge drop in ionization energy, and less so every time we go on forward. But again, it does make this N a fairly big controlling factor. So this tends to give us our big general trends. As I go across the periodic table, we're going to tend to see increases in ionization energy. Essentially, so as we go from lithium to neon, sodium to argon, potassium to krypton. However, the ionization energies tend to decrease as we go down the periodic table, helium to neon, to argon, to krypton, and similar for any relevant individual period, whether it's lithium to sodium to potassium or aluminum to gallium to indium. However, one of the big things that differentiates our ionization energy from our Z effective is we get some really big pockets of really kind of odd behavior. And one of the big determining features of this goes back to our electronic configurations. So to really understand why we have these jumps in our ionization energies, let's go ahead and look at our orbital diagrams. So in general, it's going to be much easier to remove an electron from the first electron to fill a subshell than it is to remove the last electron of a new subshell. So let's say when I'm looking at boron versus beryllium. In boron, I've got one electron sitting in that p orbital. And as we've talked about previously, p orbitals tend to have lower Z effectives than those s orbitals. So those p orbitals electrons are going to be a little easier to remove. So in general, when we go from, say, beryllium to boron or magnesium to aluminum, it's going to be a little bit easier to ionize that group 3 element because this electron is essentially sitting out in that higher energy state. We tend to see another slightly smaller increase as I go from group 5. So this is elements like nitrogen to group 6. So this is elements like oxygen. Because what ends up happening is if I've got something like nitrogen, nitrogen's actually quite happy. All of its electrons are all of its p electrons are all pointed in the same direction. I've completely filled a half subshell. Very happy sort of system. However, when I go to oxygen, I've got one lone electron sitting out there having to pair. And as we've talked about previously, whenever you have to pair electrons with different spins, you tend to pay a slight energetic penalty for that, which means that in terms of the energy stability of this electron versus this electron, we tend to see that this group 6 electron is going to be a little bit easier to remove than the group 5. And we tend to see this in our general periodic trends. So in general, as I go across the periodic table, it's going to be harder and harder to remove an electrons. However, we see a small dip when we go from group 2 to 3, and when we go from group 5 to 6. And we can use this to help identify general behaviors of elements by looking at our ionization energies. And this tends to even go not just in terms of first ionization energies, like we have here, where beryllium's harder to ionize than lithium. But notice when we go from beryllium to boron, so group 3 to group 2 to 3, we see a drop in ionization energy, similarly from 5 to 6. And again, a huge one when I go from neon to sodium. But otherwise, we tend to see a general increase in ionization energies as we go across the periodic table. But this also holds as I start pulling off 2 or 3 electrons, called the second or third ionization energies. So every time I have to remove an electron from a new subshell or a new shell, we tend to see an increase. So for example, let's take out lithium. Has a single valence electron. I can remove that fairly easily. However, the second electron has to come from that 1s shell. So it's much harder to remove. So we see a huge jump every time I have to pull an electron from a new shell. Same thing with beryllium. 1 electron, fairly easy. 2 electrons, slightly harder. 3, much harder, because that third electron comes from that core group. Because as soon as I'm pulling from core electrons, we see these big jumps. Now, boron is kind of fun, because again, first electron, fairly easy. And then I see a little bit of a bigger jump than I saw for beryllium. So the reason why we have this slightly bigger jump is because of the fact that now I went from this first electron being the p electron. Now I'm pulling from the s shell, and the first electron of any new subshell is much harder than it should be. And then another slight increase as I pull up my second s electron. And then when I go to the new subshell, huge increases. So if you're trying to figure out what an element is based on its ionization energies, a good place to look is at which point, so which electron is much harder to remove, as this will indicate we're pulling from a new shell. Also, you can look for these slighter increases, such as boron's second electron, to help indicate pulling from a new subshell, but these can be a little bit harder to spot in general. For example, fluorine, you tend to see slight increase and then a bigger increase here. But again, not quite so noticeable as when you're going to the new shell. So this is a good way to try and figure out how much an atom likes any specific electron and how tightly they're bound in. This also helps predict general behaviors. For example, the reason why lithium and beryllium so readily form cations, because these ionization energies are so low. However, this still leaves us with a big question. What about the other direction? Why does fluorine, for example, love to gain electrons so much? So for that, next time we're going to jump into the idea of electron affinity, which is the same idea, but from the reverse direction. Let's figure out how much an atom wants electrons. Until then, take care.